Hello. Hi. First, I would like to thank the scientific committee for giving me this opportunity to present that work that has been conducted at Center of Excellence in Long-Acting Therapeutics at the University of Liverpool. And thanks for the previous speakers, because you will save a lot of time for me. So, okay. So I think I will just wrap it very quickly. We have discussed before the previous speakers about the TB, importance of how to treat the TB, and the problem with the current for the conventional formulations. So really, long-acting is really needed to avoid treatment failure and drug resistance. So here I will be focusing this presentation of the work done on rifabutin, because it's potent bactericidal activity, and also it has a lower potential drug-drug interactions compared to other rifamycins. So also, I'll just rip it very quickly. The long-acting formulation of rifabutin has been developed by University of North Carolina, as Katrina mentioned, using the ISF technology. And what was interesting is, after a single subcut injection in mouse, the plasma concentration was above TB MIC and human oral semen of 150 mg for 4 months. And also the Cmax of that formulation in mouse was exceeding the Cmax of human of those 300 mg. So the aim of this research is to predict and estimate this promising long-acting rifabutin pharmacokinetics in human with an achievable injection volume using empirical pharmacokinetic modeling. So first, we started by mouse pharmacokinetic. I don't know if I can point. Okay. So we started by a mouse pharmacokinetic model. It was developed and fitted in R for long-acting rifabutin PK data of mouse to describe the rifabutin depot release kinetics and plasma concentration profile. So this depot release kinetic has been allometrically scaled to human using allometrically scaled by body size using Anderson and Halford equation. And that allometrically scaled release depot kinetics has been fitted into a 2-compartment human PK disposition model and parameterized with values taken from human IV and oral data. So the selection criteria was of the first in-human dose was by plasma targets, MIC, Cman, and Cmax following approved oral doses to reflect the therapeutic window, and using an acceptable subcutaneously human volume, which is between 3 and 4 milliliter. So similar approach has been used in KELT by our senior colleague Henry Bertinez, and he presented that work last year in CROI. And it was for allometric relationship for long-acting injectables release rates between human and rats. And as we can see from the left figure, the terminal flip-flop KAs were all faster in rat than in human across the 11 marketed intramuscular long-acting injectables. And this is in keeping with the allometric relationship based on body size of the previous mentioned equation. So faster KAs are also expected in mice than rat and human according to the same allometric relationship. So from the data itself, so as we can see from the left figure, this is the mouse data that has been fitted of a dose 18.5 mg. Using the left diagram, the right diagram, which is the 1-compartment PK disposition model with 3 first-order depot release input fractions, slow, mid, and fast. And the mid-release fraction was delayed by the transit compartment. So similar, so the scaled, as we can see from the right diagram, this is a human model, which was the same rifabutin long-acting depot release, but with the scaled parameters, and it has been fed into 2-compartment PK model. For the prediction, as we can see from the left figure, the long-acting, so we have 3 targets, as I mentioned, MIC, and Cmin of the dose 150 mg, and a Cmax, which is the highest in the red line, of dose 450 mg. But in absence of long-acting bioavailability, we simulated the PK assuming if bioavailability as shown in the dotted. I don't know if I can to point.
Just point at that. Yes, just point at the screen.
Okay. Okay. Oh.
Point at the bottom.
Okay. So, yep. Where was I? Okay. So the black dotted.
It's the top button.
The top button. Okay. Oh, okay. Cool. So yeah. So the black dotted here. It's a prediction if the lower one is if bioavailability is 50%, and then if it's 75% or 100%. So according to that, the proposed injection volume and dose was 4 milliliter first in human, with 2,200 mg, around 2.2 gram, and to be given to be split into 2 injection sites, 2 milliliter each. And this dose was chosen because it's applied with the exposure we wanted, with a Cmax 71 nanogram per ml and C average within the 4 weeks for 64 nanogram per ml and AUC 44 microgram hour per ml. So this is the dose that should be given in human, according to the prediction, every 4 weeks. So to summarize, the mouse PK data was best fitted using 1 compartment disposition model with 3 first-order depot release fraction. With optimal case, if bioavailability is 100%, we say 2,200 mg will be given monthly in human, according to 4 milliliters split between 2 injection sites. And the predicted human dose was actually less than the cumulative oral dose of 300 mg per day for 1 month, around 75%, which is, we are saving a lot by, even if the dose looks really high. So one of the reasons why we have this higher dose compared to the mouse one is that due to the low IV clearance in mice compared to human. That would be one of the reasons, plus the Ka, which is faster in mice than in human. So if we want to decrease the injection volume, we suggest to improve the formulation by increasing the drug load. And by increasing the drug load, we can decrease the injection volume and maintain the same concentration, which is 2,200 mg, or even increase the dose concentration if we want to. One last thing is we need to estimate the long-acting bioavailability to improve our scaling from preclinical to clinical PK, as the current model assumes bioavailability is 100%, which could be an overestimation. Thanks a lot. I would just thank the last my team in KELT for their contribution to that work, and people from UNC, UAB for the preclinical work, and of course Charles at the end, and LEAP for the grant for funding that project. Thanks a lot.